Assalamu alaikum. Hello, everyone. Before we start from where we left off last time, I would like to just correct something. Okay, here for the heat map for the correlation matrix. Okay, dark, the very dark one, the blackish one, actually represents the very weak correlation. Okay, so I think this heat map actually plots the absolute of the correlation. Okay, here all of them are positively correlated. We don't have one that is negatively correlated, but I think in general I need to also double check that once more, maybe with an example where we have both positive and negative correlation. But I think it plots just the absolute value. It focuses on the absolute value. So 1 and minus 1, the absolute is 1. So both are strongly correlated, okay, to that. If I have very bright color here, maybe I can say white for this one, then that means these two variables are very correlated to each other, okay? There is very strong correlation, but is it positive or negative? Maybe we don't get this information from here, okay? When it's very black, then that means there's very low correlation. Okay, the exact black one, that means the correlation is 0 between these two. Okay, so these are the absolute values. And here, in fact, if you remember, we took the absolute value and then we sorted the features based on their correlation with respect to y, regardless of the sign. Okay, x1 is the most correlated one with y, regardless of the sign. Okay, and it's already positive here, but regardless, it has the highest absolute. Okay, and x5 comes after that, and so on. That's just a quick thing I wanted to mention. Now let's come to penalized or regularized linear regression. Okay, so remember, in the OLS, ordinary least square regression, we used to minimize this term. We find the model parameters that minimizes this term, actually the sum square errors or the mean of the square errors. The errors are the difference between what we predict using our model and the actual value. Okay, so we used to listen so much to what our training data is telling us. So we're so much concerned about what our training data is telling us. And if our training data is not, our training data sums are not good representative of the whole population, we may run into the problem of overfitting. Okay, we get so much concerned about what our training data is telling us. In order to generalize better outside our training data, maybe we need to consider this loss function. It's a weighted sum between the two terms. The first term is the error, or what our training data is telling us, and the second one is a penalty or regularization term that can help us generalize better and avoid the problem of overfitting. Okay, so this we call this if you get so much concerned about what your training data is telling you and you don't generalize well outside the training data, then this problem is called overfitting. You get so much concerned about what your training data is telling you, so you overfit. Okay, so then what we are considering here is a loss function that is a weighted sum between these two terms. The first term is the loss in the training data, and the second term is a regularizer, and alpha is controlling this, how much we care about this versus that, and we will talk about how to choose alpha later on. So alpha is a hyperparameter, but we also can actually optimize it. Okay, we can find the best alpha. We will look at that later on. So to explain the problem of overfitting, I prepared an example. It's not for linear regression, okay? But it can tell you, it can explain the idea very well for you. Okay, let me go to this slide here. So here we have our training data, the red crosses here. This is our training data, okay? So we built the first model. It's a linear model, okay? So we have two parameters, beta 0 and beta 1. So we have only one single feature, x. So we come up with this line here, okay? Here you can see there's a high bias here. You will have high error in both because we are biased toward like a linear relationship. Maybe this is actually can be approximated better by a curve. Okay, but we were biased towards like choosing a linear relationship. So we will have high error both in our training data as well as in any unseen data. So the green crosses is data that wasn't used to train. Okay, so this is unseen data during the training time. So as we can see here, we can actually we are so biased here, and we will have high error for both the training as well as the outside the training data. Now let's look to the extreme case here to the right. We have actually created higher degree polynomials, okay, more features from the original one. Okay, so as you create more of these, you can actually uh, uh, create more complex curves that may fit your data very well, pass through every training data sample, okay, as you have more of these features. So for example, here we came up with this curve that passes through every single training data. So it's so much concerned about what our training data is telling us, okay. Then so we will achieve like very low error for the training data, but that is not a right thing to do because it will not generalize well outside of our training data. As we can see here for the green ones, the variance of the error can be very high. Okay, so if you test it outside the training data, you will experience very high loss compared to the loss that was achieved during the training data. So this is the problem of overfitting. Okay, so maybe it's you need just to consider the right amount, the right number of features. Okay, for example, here this is just the right one. This is like fit our data, and in fact the error can be much lower outside the training data. It generalizes much better. Okay, hopefully this explained the idea of overfitting. In the context of linear regression, I would say this can help us actually avoid problems like, for example, if you have many features, it's in general, it's good when the features are less correlated to each other and more correlated to the target variable. So if you have many features that are very correlated to each other, okay, linearly dependent on each other, then we may run into the problem of multi-collinearity, and that can confuse the model. So then maybe like introducing the penalty term on the regularizer can actually bring their weights to be low and like smooth out this the effect of this multi-collinearity problem. That's in the context of the linear regression. Also, if you have some features that are unrelated or very weakly correlated to the target variable, okay, the penalty term will actually, according to our choice, can actually kill this. According to our choice for the penalty term or the regularizer as well as the weight alpha, actually we can systematically kill these features, bring their weights to zero. Okay, and that actually can help the learning in many cases. So this is a more systematic way. You remember when I said you look at this, maybe you find like there are some features that are weakly correlated to why you can drop them. Okay, so that is a manual way of doing it, but think of this as a more systematic way to do it. Okay, so would introduce, in fact, you can find the best like you can, yeah, maybe if you like choose the right value for alpha and the right value for the regularization function, you may do better job than just manually dropping some of these features. But in general, you can actually try all the different choices. You can manually drop some and build model based on that. You can actually build different models using different choices for the penalty or the regularizer function. And at the end, you will measure the generalizability of each one of them as we will explain later, in some unseen data, and then you come up with a final conclusion, which model you should choose. Okay, we will come to that. I don't want to be ahead of the slides, but that's the idea at very high level. So now for the penalty function or the regularizer, there are many choices, but this may be the most like famous ones. Okay, there's this choice, which is the sum of the squares of the model parameters, or the norm 2 square of the model vector. Okay, that's one choice. The other choice is the sum of the absolute values, or the norm 1 of the model vector. Okay, so this is called ridge regression, the first one. The second one is called lasso regression. Okay, so each one has his advantages and disadvantages. For example, for the ridge regression, okay, if you have a small number of samples and features, you can compute a closed form solution for it. Okay, this is the closed form solution for ridge regression. Yeah, ridge regression. So let me show you how we very quickly, okay, how we can actually compute that. This is the slide here. Let me share it here. So as I said, it can be written this way, right? In the matrix format. X beta or X is the data matrix, beta is your model vector minus Y plus weight lambda here. I don't remember what was, yeah, was alpha there. Okay, and this is our 1/2 MR constants. Okay, they are not gonna change the optimum solution. The optimum solution to the sum same as the optimum solution to a constant times this sum. Okay, so now how do you compute the gradient for this one, which is nothing but X transpose times X beta minus Y plus lambda times beta, okay, because this 2 will come down and it will cancel with this 2. So this will be equal to 0, okay? This is a vector of zeros, okay? Now that's so why? Because at the optimal point, the elements of the gradient vector are all of them zeros, okay? Then just simplification, okay? X transpose X beta minus X transpose Y plus lambda times beta is equal to 0. And beta, we take beta outside here. And since X transpose X is a matrix, we introduce identity matrix here, okay? Lambda times identity. So it doesn't change anything. Lambda times beta is the same as lambda times identity times beta. So then this term, we take the inverse of that times X transpose Y. That is the optimal beta. And you also can, the good thing for ridge regression, you also can compute the gradient at every point. It's differentiable everywhere. So we can compute the gradient. So we can also run gradient descent. Okay. But for the lasso regression, okay, we cannot compute the closed form solution. And also it's not, this function is not differentiable everywhere. So we have also an issue with running gradient descent. But actually there are many well-known efficient algorithms to solve the lasso regression as well, okay? On the other side, okay, lasso actually can actually give more sparse solution compared to ridge, okay? So if, for example, if there are some unrelated uh, 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 features to what we are trying to predict, then lasso can actually bring their weights to exactly 0, okay? This ridge can reduce all of the weights, but this actually can bring some weights to be exactly 0, okay? So that's one advantage for lasso over ridge. In general, you will always try both of them with the OLS and different choices for alpha, and you validate each one of them, and eventually you will choose one that generalizes well outside your training data, as we will see later, okay? So now let's take this example here, okay? So example of a penalized regression. So we load this data and we create a data frame from the data of this file. And here we extract both the input features as well as the target variable. So the input features are all columns except the last one, okay? And the target variable is the last one. And then here we import ridge regressor from scikit-learn and .linear models. We pass alpha here, okay? So we want to build a regressor using this value for alpha. We will come later on how to find the best alpha, okay? So here we created the object, and here we fit the regressor into using our input features as well as the target variable, okay? So here we have trained the model. But after this point, we have trained. When we run this line, then we train the model. As you can see here, we pass the input features. We don't append the feature of all ones. This is done Python is doing that for us, okay? So then we can compute and come up with the here. So the best value for beta 0, the intercept is equal to 0, and these are the values for the weights. okay, beta 1 all the way to beta n. As you can see, their values are very low compared to what we had with the OLS. If you go up with OLS, okay, OLS is a special case when alpha is equal to 0, right? When we actually cancel this, because when alpha is equal to 0, that goes to 0. We only focus on this, right? So when alpha is equal to 0, these were the values. As you can see, when alpha is equal to 500, they went too low, okay? Maybe this is very high value for alpha, because go back here. If alpha is very high, okay, then we care about bringing all of the betas here. Look at this here. First, when alpha is very low, the extreme case when alpha is equal to 0, then this reduces to all less. So we only consider the training error. Okay, so we only consider like we are so much concerned on what our training data is telling us. Now, when alpha goes very high, then we are not listening to our training data. We are just bringing all these to be very low, the weights. So alpha needs to be chosen very well. Okay. So now if I, for example, make alpha equal to 1, it will be a point in between, okay? Okay, so now let's just keep the original one, okay? Now let's come to this here, okay? So this is lasso, so we import lasso, we do the same thing, okay? Then we create the regressor, alpha here is 0.05, and we fit that using our data, and this is what we get, okay? For 0.05, this is what we get. If we do, you see, some of them, as you can see, they are brought down to 0. Okay, exactly 0. We kill some of them. Okay, so if we go higher, we kill more. Okay, as you can see here. Okay, so in alpha is equal to 1, all of them are 0. That's too much. Okay, so when alpha is equal to 0.5, only the first one is considered. All the others are brought down to 0. So when alpha is equal to 0.5, that means all matters for predicting y is uh, the first feature. As I said, you will try different alphas and see which alpha gives you a better generalizability error when you test it on a data that is not used to train the model. We will look at that later on. So let's read through this. Are the coefficients different from OLS? What can you infer? Yes, they are different. Okay, as we saw here. Okay. Now OLS versus Ridge. OLS and Ridge have all non-zero coefficients, and we saw that. Like this brings them to be very low, but all of them are non-zero coefficients. Okay, so how the coefficients given by Ridge are less. They are both non-zero, but the ones we got when we used Ridge regressor are much less compared to the OLS ones. Okay, OLS versus Lasso. OLS has, as I said, all non-zero coefficients, but for Lasso, there was only one non-zero coefficient when alpha is equal to 0.5. Okay, so then Lasso claims that only the first column is relevant to the output variable when alpha is equal to 0.5 for this choice of alpha. Okay. Okay, lasso versus ridge summary. Ridge regression shrinks the estimate values. It's useful when there are correlated input columns. When there are linearly, not in general correlation, I would say, when there are linearly dependent columns, okay, very like dependent on each other, then the like ridge will bring the weights will to be low, so it can overcome the problem of multi-collinearity. Okay, Lasso does feature selection because it's actually killing the unrelated ones. Okay, so it brings their weights to P0. Okay, in general, which one to use? Okay, you can just you try both of them at different choices of alpha and then choose the best. Okay, the quality of the solution depends on the value of the hyperparameter alpha. It plays very crucial role in defining like what's the best model. Okay, selecting the best value for alpha generates better results than OLS. Okay, because actually OLS is you think of OLS as a special case. It's a corner case when alpha is equal to 0, okay? So if that's the best case, then you choose alpha equal to 0. Here you will achieve that, okay? Okay, now how do you actually, like here we trained the model for a given value for alpha, okay? Now, how can we actually validate our model parameters as well as the hyperparameters, the choices, because the hyperparameter is a choice we make, okay? So to explain this, let me come here, okay? So in general, okay, so we can split the data into training and testing, okay? You train different models, okay? Different models here. Lasso with different choices for alpha, as well as Ridge with different choices for alpha, and OLS. You train all of them, and then you test them in the testing data set. The testing data set is a data set that wasn't used to train the model, but for every sample, we know the value for the predicted variable. So we know that, okay? So then we use it to test the model. So it shouldn't be used to train the model. We use it to test. So we test all these different models. The one that achieves the lowest loss, the lowest loss in the testing data. When I say loss here, is this part only, okay? We don't consider the penalty term in that. We consider only this for all the algorithms, including the ones that were trained using the penalties, adding the regularization. So this is the loss. Okay, we compute this loss, okay, in the testing data set, and the one achieves the minimum loss in the testing data set, we choose it as our final model, okay? But now the issue here is like somehow we have used the testing data set in order to also make a choice for the hyperparameter, because which the best model is like, because we have trained different different models by changing the hyperparameters. So another way where the testing data set is left away from all of these, it doesn't contribute to learning the models as well as the hyperparameters, is to divide the data into training, validation, and testing, okay? Now you train the model, okay? You start with initial value for alpha, usually start with a small value for alpha if you're considering Lasso or Rich, okay? For these two, you start with small value for alpha, you start with a small value, you train, and then what you do, you train, then you validate that choice of alpha using the validation data set. So you train here the model parameters, you come up with the choice for the model parameters for that given alpha, you validate it here. Now, if you find like the error in the validation data set, and again, the error is this term, okay? If you find the error in the validation data set is greater than the error in the training data set, and again, even like after you train, even if you train the regularized version, when you compute the error later, or the training loss at the end, you compute it using only this term here, and then you compare the training loss with the validation loss. Let me go back here. So you train for a given value for alpha, you compute the training loss, you compare it with then you validate your data in the validation data set, and you compute the validation error or the validation loss. If you find, for example, the training loss or the training error was low, but then when you move to the validation data set, the validation error or loss became high, then most probably you are running in the problem of overfitting, okay? You are so much listening to what your training data set is telling you, and you're not generalizing well outside of that. Then what you do, you increase the value of alpha, okay? You go to higher alpha. You increase the value of alpha, and you do it again. You keep iterating between the training and the validation until like the validation error achieves its minimum. You cannot improve it any further, okay? Then that's it. That's the model, the model that achieves the minimum error in the validation data set, okay, regardless of because you're going to test that for all different choices of the penalty, this as well as that, and then you will pick the one like you will train Ridge with different values for alpha, because you're changing alpha for that as well as for the lasso. Eventually you choose the one that achieves the minimum loss in the validation data set, then you test that on the testing data set to report the generalizability error. So testing data set should not be used to train the model, to learn the model parameters, as well as to learn the hyperparameters. It's just like a data that didn't contribute to the learning process, you test your model on it to report your generalizability error for your model. Okay, that is that summarizes this actually here. There's also another way to do cross validation. Okay, if you have like limited number of samples, because here you will split the data, for example, 60%, 20, and 20. Okay, so you're training only on the 60% of the data. But if you have limited number of samples and you don't want to like sacrifice this 20% for the validation, you can do actually like what we call cross validation, and there are different ways to do that. I will explain. There are, as I said, there are different strategies. One of the well-known ones is k-fold, and since we are going to use k-fold later on in this topic, I will explain k-fold here. Simply, you have all the data, you split the data into training and the testing data, so you leave this testing data aside. And for the training data, instead of further splitting it into training and validation, you actually, what you do, you actually like create these folds here. Here it's 5-fold, okay? So for the first split here, you train the model using these fold 2, 3, 4, and 5. These are like, as I said, it's k-fold. So you're splitting the training data into these subsets, okay? Equal size subsets. For the first one here, you train your model using these folds, and you validate it using this one. For the second one, you train using fold 1, 3, 4, 5, and you validate using fold 2 for every choice of the hyperparameters, for every choice of alpha. So you train this, and then you take the average of the loss, okay? And you will compare different algorithms using the average. And the one that achieves the minimum average is the one you will test on the testing data to report the generalizability error or loss. Okay, that's at very high level. And as I said, there are different ones. Like for example, leave one out. This is a special case of k-fold where what you leave out is one sample. Okay. Maybe we stop here for today. Next time we will spend some time in this case study that explains more like it's a more of another example, but just we are gonna go in details, and we will do this cross validation. We'll split the data into training, validation, and testing, and we will actually work with like how to also optimize how we will learn how to actually end up choosing the best alpha for your model. With that, I come to the end of this lecture. Thanks for watching. See you next time, inshallah. Assalamu alaikum.